Welcome to lecture 5 of module 4. We are still continuing with our discussions on various correlations for finding out the values of convective heat transfer coefficients and for different geometries, for different flow situations. Already we have seen in the last couple of lectures that convective heat transfer correlations for heat transfer in the cases of internal flows, that means flow through certain devices, which could be tubes, which could be non-circular ducts. Now, today we will see in this lecture that how the different correlations are available for external flows for the heat transfer coefficients. Also, we will try to see some problems on that. So, our topic of discussion today is correlations for heat transfer coefficient in case of external flows. Now, regarding this external flow, as we understand that external flow means that the flow over a plate, over a tube, across a sphere, something like that. So, in first case we will see that flow over a flat plate. So, certain interesting issues are there when there is a conception of flow over a flat plate. You will just try to see, we will discuss in details later on when we will be discussing about the different boundary layer theories and all. A fluid is flowing like this. When it starts flowing, then it develops some layers, which is these are called boundary layers. Okay, we will discuss these issues later. So, this initial region, this region is called laminar region. This region is called turbulent region. And this is the direction of, this is the fluid flow, and this is the plate length. Okay. So, turbulent region, and we can see that as we go along the length of the plate, the flow behavior is changing. So, flow behavior changes from laminar to turbulent region. Okay. And we know that a flow behavior of a fluid is very nicely characterized by Reynolds number. Okay. Reynolds number. And we have seen that particularly for flow through pipes or tubes, we have seen that Reynolds number is defined as d V infinity rho by mu, or sorry, here the concept of V infinity does not arise here. It's a V average velocity like this. So, this becomes the Reynolds number based on the diameter of the tube or pipe, where d equals to d equivalent in case of non-circular ducts. Okay. Now, in these situations, when there is a flow over a flat plate, the question arises that how is the characteristic length, because this d is the diameter of the tube or the inner diameter of the pipe or the equivalent diameter, this becomes the characteristic length. So, in Reynolds number there is a term that is called characteristic length, and this is the characteristic length d. Now, what happens to the characteristic length here? And another thing that there is in place of the velocity like average velocity and all these things, there is one velocity here that is called free stream velocity here, the V is equal to V infinity, which is called free stream velocity. Already we have discussed little bit on that free stream velocity means the velocity which is free from the stream of the velocity of the stream which is free from the effect of the wall. That means that any flow beyond this boundary layer has a velocity which is V infinity beyond the boundary layer, it is free stream. So, here velocity remains the constant. So, it is the velocity of the fluid is not in this region. In this region, it is not affected by the wall of the tube. That is the main reason, main considerations here. Okay. So, therefore, the Reynolds number in the present situation for flat plate the Reynolds number flow over a flat plate, the Reynolds number is given as say Re, we can tell it to be infinity based on this free stream velocity. We will say that x, Rex, this is equal to x V infinity rho by mu. Now, we can understand that this x is that distance from the leading edge. So, this is the leading edge and this in this direction this is the x. So, at any location we are getting a value of Reynolds number. So, even though one important thing here, even though the free stream velocity remains the constant, okay, where that effect of wall is not there, but Reynolds number is a variable quantity with respect to length from the leading edge. So, as because Reynolds number is a function of x, x is the coordinate at any particular location of the plate. So, therefore, this is also called as local Reynolds number. And what happens in case of flow over a flat plate, that as because this is local Reynolds number, the initial stages, that means towards certain length of the plate from the leading edge, the flow is laminar, as we can see from the figure. In this region flow is laminar, and then there is a transition that takes place here. This is the transition zone and this is turbulent region that happens. So, by change of x from the leading edge, the values of Reynolds number will change, and that will finally dictate that whether the flow is laminar or turbulent. Okay. Now, what happens to be the case is in general that the flow over a flat plate is said to be laminar, because there can be lot of issues. I will come to that. Said to be laminar when Rex is less than 5 into 10 to the power 5 and turbulent when Rex is greater than 5 into 10 to the power 5. Now, these are very this is not very hard and fast values, but that it is understood that when the Reynolds number, local Reynolds number is nearby this region, there is an expectation that a transition from laminar to turbulent flow will take place when the flow is over a flat plate. Okay. Now, it has been found that these things, these values, this 5 into 10 to the power 5 values, or these critical values of the Reynolds number where the turbulence takes place, it many a times depends upon the surface roughness and various flow disturbances due to various other reasons. So, that means when the surface roughness is also a reason for the disturbance of the flow on the flow. So, when more the surface roughness, it will give more turbulence into the flow situation. So, you can have an early turbulence in the flow. So, therefore, it is said that when more disturbances are there, then turbulence can even happen with a Reynolds number as low as 10 to the power 5. For large disturbances, turbulence can happen at Rex nearly equal to say 10 to the power 5. Forget about 5 into 10 to the power 5, it could be 1 into 10 to the power 5. So, that is what it is I was trying to say that it is not very hard and fast, it is the subject to certain discretions, subject to certain decisions. Okay. Similarly, for flows which are very free from fluctuations, okay, the turbulence may not start until Rex equals to 2 into 10 to the power 6. So, this is one interesting point. So, when you have a very smooth flow, there is little disturbances, the plate wall is less rough, then we can have even the transition even at later stages of the length of the pipe. So, this boundary layer, this profile that can be dependent on the those surface roughness and flow disturbances due to various other reasons. Okay. Now, what we will see is that as we can understand that there are two very distinct category of flows. One is that laminar flow, another is turbulent flow. Yeah, transition region, this is a very complicated area. So, we won't discuss much about those regions. So, in case of a flow over a flat plate, also we can distinguish it into two different aspects. One is called for laminar flow, and another would be for turbulent flow. Okay. Now, if we see for laminar flow, and for say constant wall temperature, we have like Nusselt X. We can understand that Nusselt number is also becoming a local Nusselt number. We will discuss this. Nusselt X is equal to 0.332. This is a very well known relationship of Reynolds to the power half into Prandtl to the power 1/3, where we have 0.5 less than equal to Prandtl and less than equal to 50, and Reynolds number, we know that Reynolds number is less than 5 into 10 to the 5, that is the laminar flow region. Okay. And one thing we can say here, that Nusselt number is also called local Nusselt number, and this is equal to Hx x by k. So, we can understand Hx is that heat transfer coefficient at point x. So, heat transfer coefficient is a function of x. So, as we go along the length of the plate, the convective heat transfer coefficient will vary. So, this Hx is called local heat transfer coefficient. So, therefore, when we have a value of say h value will be is a function of x, and this value will go on changing as we go along the path of the flat plate. So, many a times it is used as an average value of heat transfer coefficient is used to find out the value of the heat transfer coefficient, and finally to find out the value of the heat exchange. Okay. Now, in this particular correlation, this relationship is obtained from an approximate solution of the boundary equations of momentum and energy. In subsequent lectures, we will discuss about the boundary equations in the boundary layers. We will discuss those issues. Now, the fluid properties are measured. This is very important. While we will be using any correlations, one thing we have to understand that what is the temperature at which the fluid properties has to be evaluated, because some of the fluid properties can be drastically changed due to the changes in the temperatures. So, should be very careful about that particular issue. So, here the fluid properties are evaluated at TF. TF means film temperature. We have already discussed this, and film temperature is, we know that wall temperature plus bulk temperature. Here the bulk temperature is nothing but the free temperature, free stream temperature. So, it is TW plus T infinity by 2. So, it is the arithmetic average of wall temperature and free stream temperature. So, TW is the free wall temperature and T infinity is the free stream temperature. So, arithmetic average of that is nothing but the film temperature. At that temperature, we have to evaluate all the fluid properties to get the values of Reynolds number, to get the values of Prandtl number, and also to get the values of thermal conductivity, okay, to get the values of heat transfer coefficient. So, now if we see that from this expression whatever we have written, we will find out the values of local Nusselt number, and we will find out the values of H, local heat transfer coefficient, if we have the ideas about these all other properties. So, under that situation, if we try to know the average value, so average heat transfer coefficient this is basically a value of heat transfer coefficient averaged over the entire length of the plate. Why it is entire length of the plate is being told? Actually, it is averaged over the entire area of the plate, because that heat transfer coefficient, that this convective heat transfer is taking place from the surface of the plate. So, it is the total average over the entire surface should be there, but if we consider the length and width is equal to unity, so it is effectively it becomes like average its entire length, but actually it is over the entire area of the flat plate. Okay. So, if we say then H bar is equal to 1 by W into L. L is the length of the plate and W is the width of the plate. Okay. And this width of the plate is a constant. So, if we consider that, say this is the width of the plate. So, this is the W. So, our point of interest is the flow is in this direction. So, flow is in this direction. So, flow Reynolds number is changing along the length. So, this is x. So, this the total length is L. So, it is this, and this is remaining fixed. So, all the point along this width direction is the velocity remains the same. So, that does not change. So, at any particular length along the width, the velocity remains the same. Okay. So, therefore, so if we say this, H is a bar is equal to this integration of 0 to L Hx into W remains the W into dx, because for any strip, differential strip, if we do the integration. So, this is becoming dx and this is becoming W. So, the differential area in this region is W into dx, and this W cancels. So, therefore, our integration limit will be from 0 to L. Okay. So, therefore, it becomes 1 by L 0 to L Hx into dx. So, this is the expression that is used to find out the values of average heat transfer coefficient. And now, how to get the expression of Hx here? We can see from the Nusselt number expression, it is a function of x. So, we have to put that over here and get the value of average heat transfer coefficient is like that. So, what we will have? H bar is equal to 1 by L 0 to L 0.332, okay, and the Reynolds number is x into V infinity rho by mu whole to the power half into Prandtl to the power 1/3, and then we have Hx is equal to this, and we have if we see here that into K will be there, K by x will be there into dx. So, Hx by K. So, Hx by K is equal to this. So, if we see, if we go back previously, you will see that Hx will be represented by 0.332 Reynolds x to the power half, Prandtl to the power 1/3, okay, and then Hx will be equal to, also there will be a k by x. So, k by x this. So, this is becoming the expression, and then we have to go for integrating these. All other parameters are constant, except it's a matter of is a value related to the x to the power minus half. Other things are constant. Okay. So, from this we can find out that this is equal to 0.664 k by L V infinity L rho by mu whole to the power half and Prandtl to the power 1/3. So, this is becoming actually 0.664 k by L Reynolds L. Now, here x is replaced by L. So, it is becoming the Reynolds number with respect to length of this. So, this is the Reynolds number at x is equal to L. So, we should be very careful. So, average value of heat transfer coefficient we are getting when the Reynolds number value is calculated based on the length of the tube, length of the plate and Prandtl to the power 1/3. And this way, if we see, then if we take this part in the other side, okay, in this side, then we will get we will write now Nusselt. So, this is becoming average Nusselt number because it is based on average heat transfer coefficient. So, this is also called as average Nusselt number. Okay. And this is becoming equal to h bar L by k. So, Hx is replaced by x, Hx is replaced by h bar, x is replaced by L, k remains as k. So, this is equal to 0.664 into Reynolds to the power half and Prandtl to the power 1/3, and thus we can see that NUL average Nusselt number is becoming equal to twice Nusselt number at x equal to L, because Nusselt number expression is, if we put x equal to L, then what we will be getting. So, it is twice of that values. That is what we are going to get. Now, exactly similar way we can find out the case for turbulent flow situation. So, for turbulent flow over a flat plate, again we are discussing on over a flat plate. So, for turbulent flow over a flat plate, we have an expression for Nusselt number NUX. Again, it is a local Nusselt number. NUX is equal to 0.0296 into REX. Reynolds number to the power 4 by 5. We can see that is the power is different, and Prandtl to the power 1/3. So, Prandtl number power is not changed, but the Reynolds number power is substantially changed, because we know that initially it was Reynolds to the power half, now it is Reynolds to the power 4 by 5. There is one relationship, because we have to understand, higher the flow, higher will be the turbulence, higher the turbulence, better will be the heat transfer, and better heat transfer means higher will be the heat transfer coefficient. So, when we will be having some Nusselt number expression, then it is expected to have a higher power for Reynolds number. Okay. And here 5 into 10 to the power 5 is less than REX, less than 10 to the power 7, and 0.6 is less than Prandtl and less than 16. Okay. Now, exactly in the similar way as we have seen in the previous case, if we do the integration, we can get the average Nusselt number average Nusselt number also in this case. So, average H bar will be getting 1 by L 0 to L again Hx dx, and this will be equal to 1 by L 0 to L 0.0296 REX to the power 4 by 5 into k by x into Prandtl to the power 1 by 3. And from there we will get the Nusselt number NUL average Nusselt number. Average Nusselt number, again I am repeating that it is based on the average heat transfer coefficient. Okay. So, this is equal to 0.037 Reynolds based on the length, total length of this pipe, again to the power 4 by 5 into Prandtl to the power 1/3. So, this is becoming the equation when you have a turbulent flow situations, and this relationship that for turbulent flow situation, this relationship, as we know that in case of turbulent flow, the analysis of mechanism of flow of heat transfer is really difficult, because the flow behavior itself is a complicated one. So, therefore, the previous expression whatever we have written for turbulent flow, that expression is generated by taking the help of analogy or analogical behavior between fluid friction and heat transfer. This analogical behavior will be discussing in subsequent, maybe in the next lecture we will be discussing these analogical behaviors, okay, and the importance of the analogies and how the fluid friction analogy is used for getting the values of mass transfer coefficient, or sorry, heat transfer coefficient in the present situation. Okay. Now, we have discussed the correlations which are available for flow over a flat plate, and also we have discussed, try to discuss that how to, what is the Nusselt number definition in case of flow over a flat plate, and how to discuss about this laminar flow region, how to discuss about the turbulent flow region, how to, what about that heat transfer coefficient, and how to get the average heat transfer coefficient. Now, we will discuss the next thing is that flow across cylinder. So, when we are telling about the flow over external flows, so we told about this flat plate. Now, we will see the flow across cylinders. This is a very important issue, flow across cylinders. So, there are various correlations available to find out the values of flow across cylinders. We will be quickly discussing some of the important correlations which are available. First one is that is being developed based on the experimental data by Hilpert, for gases, and Nordsen and Katz for liquids. Based on this experimental data, we have this, that NUD, Nusselt based on diameter. Here we have to understand that this D is the diameter of the tube we are considering. Nusselt diameter is equal to some constant C into RED to the power n into Prandtl to the power 1/3. So, we can understand the this n values are function of C and n are dependent on some Reynolds number. So, RED, if we give RED and C and n, so for different values of RED, so 0.424, C is equal to 0.989 and n is equal to 0.33. For 4 to 40, this is 0.911. So, C is more or less constant in the initial stages, and this is 0.385, and then for 40 to 4000, you can see here now there will be changes because it is now changing, the Reynolds number is going very high. So, it is becoming 0.683, and this is 0.466, and then between 4000 to 40,000 is becoming 0.193, and here it is 0.618. We see that index is gradually increasing and the constant term is gradually decreasing, and then 40,000 to 4 lakhs. In this Reynolds number region, it is 0.0266, and here it is 0.805. So this is these are the different values of the coefficients based on the values of the Reynolds numbers, and these are different values of the power of the Reynolds number. Okay, and one thing is here that the fluid properties are the film temperature, fluid properties at TF. We can understand here the TF means that free temperature of the fluid and the wall temperature of the tube. So, TW plus T infinity by 2. Again, the Reynolds number is based on the cylinder diameter and piston velocity. So, RED is, you can say that d V infinity rho by mu. So, d is the diameter of the tube, V infinity is the piston velocity, rho and mu are the properties of the fluid, and these are to be evaluated at film temperature. Okay. Now, Fand has given an expression. According to Fand, the heat transfer coefficient NUF is equal to 0.35 plus 0.56 REF to the power 0.52 sorry 0.52 into Prandtl F to the power 0.3. So, here interesting point is that the suffix F indicates the fluid properties to be evaluated at TF. Fluid properties to be evaluated at TF. That is the indication of this point F here, suffix F here, and REF is equal to, we have again said that d V infinity rho by mu, and you can say that these are F. Okay, so F indicates that it is there to be evaluated at film temperature, and 10 to the power minus 1 less than REF and less than 10 to the power 5. Again, this Reynolds number is based on the diameter of the pipe. Okay. Then Zhukovskas has given some relationship, which says that Nusselt is equal to some constant C into Reynolds to the power m into Prandtl to the power n and Prandtl by Prandtl W, that is, you can understand the evaluation conditions is represented over here. So, here for Prandtl less than 10, n is equal to 0.36, and for Prandtl greater than 10, n is equal to 0.37. So, these are minor changes, but all properties to be evaluated at TB, average temperature, average bulk temperature, except PRW at wall temperature. TB bar is the average bulk temperature that we have already discussed, and that values of C and M can be found out like this based on the Reynolds number. So, if we have Reynolds number here, C here and M here, we can, from the table we can find out for 1 to 40 Reynolds number, it is C is 0.75 and this is like 0.4, and from 40 to 10 to the power 3 it is becoming 0.51, and here it is 0.5, then 10 to the power 4 2 into 10 to the power 5, it should be 4, and this is say 0.25 0.26 and here it is 0.6 and then 2 into 10 to the power 5 to 10 to the power 6 in this level. This is 0.076 and this is 0.7. So, this table gives an idea about that usage of this equation given by Joukowskas, and it says the values of the coefficients and other constants m for different situations of the Reynolds numbers. Okay. Now, what we will discuss some more equations we will be just quickly looking into is given by, say, for flow through tubes. For example, for heat transfer from tubes in cross flow, for heat transfer from tubes in cross flow, okay, for both liquids and gases, Eckert and Drake proposed. What they proposed? Nusselt equals to 0.43 plus 0.50 Reynolds to the power 0.5 into Prandtl to the power 0.38 into Prandtl F by Prandtl W, okay, to the power 0.25. Here this is for Reynolds 1 less than Re less than 10 to the power 3, and another equation is Nusselt equal to 0.25 Re to the power 0.6 Prandtl to the power 0.38, again Prandtl F by Prandtl W to the power 0.25 here for 10 to the power 3 less than Re less than 2 into 10 to the power 5. So, these are the situations. So, two different values ranges of Reynolds numbers, okay, the Nusselt number values are calculated. Now, for liquids, fluid properties are at free stream temperature, you can say this T infinity except PRF and PRW. As we understand, PRF and PRW are to be evaluated at TF and TW. That is the film temperature and the wall temperature. Okay. And for gases, fluid properties are at film temperature, then the Prandtl ratio, PRF by PRW may be dropped or assumed to be 1. So, this is what is that proposed by Eckert and Drake, and then we will see a few more for flow. So, more comprehensive relationship that is given by Churchill and Bernstein. They are giving actually these relationships when we are going for more and more complicated relationships, they will be marginally improving the predictions of the heat transfer coefficients, but at the cost of some more time, more rigorous calculations of the heat transfer coefficients. Okay. So, that Churchill and Bernstein has given this expression as Nu D equals to 0.3 plus 0.62 RED to the power half Prandtl to the power 1/3 divided by we can see 1 plus 0.4 by Prandtl whole to the power 2/3, okay, and the whole to the power 1/4. This is a very complicated expression. This is 1 plus then RED by this some value 282000. Okay, this part whole to the power 5 by 8 and this whole to the power 4 by 5. We can understand that how complicated that equation is, but this is definitely going to give much better result if somebody takes care of these equations for his calculations. So, then this is for 10 to the power 2 less than RED. RED from the name itself we can understand that it is based on the diameter of the tube and into 10 to the power 7, and PED is the Peclet number, which is nothing but RED into Prandtl number. This is equal to RED into Prandtl number. We have already discussed what is Peclet number, and that should be greater than 0.2. Under that situation, this is this case, and this equation has been underpredicts the data when RED is between 20,000 and 4 lakhs. So, then what they have given? They have given a new correlation for this range when an NUD equals to 0.30 plus 0.62 RED to the power half Prandtl to the power 1/3, and then we have the same thing 1 plus 0.4 by Prandtl whole to the power 2/3 to the power 1/4 into 1 plus, here is the change, RED by 282000 whole to the power half. This is the change, and there is no further power here. So, there is the change, and the condition is that 20,000 is less than RED is less than 4 lakhs and PED is greater than 0.2. So, these are the conditions for these equations to be applicable, and then there is one more equation that is given by Whitaker for Whitaker equation for tubes. Okay. So, NU Nusselt is equal to H bar average heat transfer coefficient into D by K, and this is equal to 0.4 RE to the power 0.5 plus 0.06 RE to the power 2/3, okay, into Prandtl to the power 0.4 into mu infinity by mu W to the power 0.25. Okay. So, for this is applicable for 40 less than Reynolds less than 10 to the power 5 and 0.65 less than Prandtl less than 300 and 0.25 is less than mu infinity by mu W less than 5.2. From the name itself we can understand that all properties at free stream temperature, okay, except that of mu W. So, mu W it is at wall temperature. So, finally, when Peclet based on diameter is less than 0.2, Nakai and Okazaki proposed Nusselt based on diameter, this is equal to 0.8237 minus ln, this is some interesting, PD to the power half, okay, and then whole to the power minus 1 for PD, already we have told less than 0.2. And the properties are evaluated at film temperature. Okay. Now, what we will do is, this is what about that for correlations for flow across the tubes. Now, we will see the 4 correlations for flow across spheres. That is also another geometry, and for that the very first one is by Macadams. He has proposed, recommends the relationship from a sphere to a flowing gas, the relationship. So this is the heat transfer situation. Okay. So according to Macadams, that H d by Kf. So again this F indicates that it is measured about at film temperature. This is equal to 0.37, then V infinity d rho f by mu f. Okay. And this is whole to the power 0.6, where 17 less than RED. So here D is the diameter of the sphere, that is of consideration, is less than 70,000. Okay. Then we have Achenbach. They have for a wide range of Reynolds number for air, they have shown for wider range of Reynolds number for air with Prandtl is equal to 0.71. They have given the Nusselt equals to 2 plus 0.25 plus 3 into 10 to the power minus 4, Reynolds to the power 1.6 whole to the power half, this is for 100 less than RE and less than 3 into 10 to the power 5. Okay. And also another relation for a different Reynolds number, Nusselt equal to 430 plus ARE plus BRE square plus CRE cube, where this is for 3 into 10 to the power 5 less than RE less than 5 into 10 to the power 6, and here A is equal to 5 into 10 to the power minus 3, B equals to 0.25 into 10 to the power minus 9, and C is equal to minus 3.1 into 10 to the power minus 17. So that almost is negligible, RE cube. So now this is what is the relationship that is given by Achenbach, and then Kramer proposed for flow of liquid past spheres. So that means heat transfer is taking place for a situation when is flow of a liquid taking place past the sphere. Then according to the Kramer, H d by Kf, again we can understand this is the evaluated at film temperature. This is equals to into Prandtl f to the power minus 0.3 equals to 0.97 plus 0.68 into say REF to the power 0.5, and here 1 less than RED F. So you can say RED F is less than 2000. So RED F means based on diameter of the sphere and based on film temperature, the properties to be evaluated at film temperature. And then two more relationships, that is by Villet and Leopard. They have said that from sphere to oil and water for heat transfer from spheres to oil and water over a wide range of Reynolds number, and that is 1 to 2 lakhs. They said that nu into Prandtl to the power minus 0.3 into mu w by mu to the power 0.25, and that is equal to 1.2 plus 0.53 into RED to the power 0.54. All properties, properties are at free steam at T infinity free steam condition except mu w at Tw, that is the surface temperature of the sphere. And then Whitaker, he has said that a single equation for gases and liquids flowing past spheres. So, according to them, that Nusselt is equal to 2 plus 0.4 RED to the power half plus 0.06 RED to the power 2/3, okay, into Prandtl to the power 0.4 into mu by mu w. Okay. To the power 1/4, where 3.5 is less than RED, is less than 8 into 10 to the power 4, and 0.7 less than Prandtl, less than 380. Properties at, so you can say it is infinity, properties at T infinity except mu w at T w. So, this way we got some ideas about that different correlations available. Now, we will just discuss quickly a problem related to some heat transfer on this. Say the problem 1, it says that in a cooling tower, the average diameter of water drop from the water spray is 2 millimeter. The air velocity with respect to the water drop is 1 meter per second. Air is at 1 atmosphere and 20 degree centigrade. Water drop is at 75 degree centigrade. Find the convective heat transfer coefficient. So, if we try to use this, a case of sphere and fluid air. So, if we try to use the McAdams relations, McAdams relation says that we have seen H d by Kf equals to 0.37 into V infinity d rho f by mu f to the power 0.6 for n 17 less than RED less than 70,000. So, we have to now find out that if you have to apply the McAdams relationship, we have to find out the film temperature Tf. So, we can see that Tf is basically wall temperature plus fluid temperature. So, it is a 20 degree centigrade fluid temperature plus water vapor temperature 75 degree centigrade by 2. So, it is becoming 47.5 degree centigrade, and we have to get the values of the different constants at that temperature. So, at 47.5 degree centigrade and 1 atmosphere pressure, because it is air, we can have we should mention the pressure over here. So, rho is equal to 1 kg per meter cube, Cp is equal to 1.0 kilojoule per kg per Kelvin, K thermal conductivity is equal to 0.0278 watt per meter per Kelvin, and then mu equals to we have 1.97 into 10 to the power minus 5 kg per meter per second, and thus Prandtl number is becoming 0.707. if we put the values, is equal to mu Cp by K, and Reynolds number based on the diameter is equal to rho V infinity d by mu, and this value is becoming 101.5. So, it is in the range. So, Reynolds number is in the range, and McAdams equation is applicable, and then what we can do is we can find out this relationship H will be from the equation 0.37 into 10 Reynolds number to the power 0.6 into K by D. K is equal to 0.0278 by D is equal to 0.002. It is a 2 millimeter diameter. So, this value is becoming 82.24 watt per meter square per Kelvin, and we can see that the same evaluation if we use by other equations, say by Achenbach equation. If we try to find out, then according to this, Nusselt equal to 2 plus 0.25 plus 3 into 10 to the power minus 4. We have just discussed this equation, Reynolds to the power 1.6 whole to the power half. This is for 100 less than RED less than 3 into 10 to the power 5. It is, and Prandtl is equal to 0.71. Our Prandtl number is very close to this, and Reynolds number is also very close to 100. So, it is applicable, and then it is becoming 2 plus 0.25 plus 3 into 10 to the power minus 4 into 101.5 to the power 1.6 whole to the power half, and this value is becoming 2.86, and then H is becoming 2.86 into 0.0278 by 0.002, and this will be 39.7 watt per meter square Kelvin. So, we can see that here in this case we got H is equal to 39.7, and the previous case we got something around 82.24. So, there are some variations in the evaluations of the heat transfer coefficient, whatever the heat transfer coefficient relationship we are using for heat transfer coefficient evaluations, though the order of magnitude remains more or less the same, but there is a wide variations in the same order of magnitude. There is a wide variations in the heat transfer coefficient values when we calculate by different empirical correlations. This problem is just to demonstrate that yes, we may come up with variations in the evaluations of the heat transfer coefficients. So, choice of appropriate correlations to find out the heat transfer coefficient value for a particular specific problem is really of challenge, and in cases we have to see if we are not proper, then we may come up with either a over design or an under design of a heat exchanger equipment. Okay. So, this is all for today. In the next class we will be discussing on the different heat transfer correlations available for say flow through packed beds and fluidized beds, as well as we will try to see that analogical behaviors as we discussed, and we will also take up a few more problems related to the convective transfer correlations. Thank you very much.